Okay, so in this video we're going to focus on Lie algebras that naturally arise when you look at Lie groups. So in the last video we introduced the notion of a Lie group, which is a group of which the underlying set has a structure of a smooth manifold. And we've seen that on such a manifold one can look at the elements in the vicinity of the identity, and there they give rise to tangent vectors at the identity element. And these are the generators of the group. So if I have a two-dimensional Lie group, I would have two generators that span the tangent space at the identity element. And we've seen that we can use the exponential mapping to go back from this tangent space to the Lie group itself. So where the exponential mapping is defined by just taking the exponential of a matrix, which is defined by taking the Taylor expansion of the usual exponential. So the sum of m equals 1 to infinity, 1 over m factorial, and then the mth power, so the mth matrix power of A. Okay, so this defines a mapping, the exponential mapping, from the set or the linear combinations of generators. So combinations alpha A x A, where alpha is, say, an n-dimensional vector, to the Lie group G. Or, to be more precise, since we're always working in a representation of G in a set of matrices, we denote this as the image of G under the representation. Okay, and we notice that actually this mapping is surjective, so any element here can be obtained by the exponential of some linear combination of generators on this side. Okay, so let's focus now a bit on what happens when I take the exponential of some generator and then I look at the group structure in G. So note if all the generators of my Lie group commute with each other, so the commutator vanishes, and I look at some linear combinations of these generators, so alpha A x A, and B is maybe beta A x A, and I look at their exponentials, they satisfy that the exponential of A, group multiplication, exponential of B, okay, this is just matrix multiplication since I'm looking in the representation. Well, just plugging in the definition, it is just the usual definition of an exponential. And now A and B commute as matrices. So I can just pull through all the terms of A to the other side and find that this is the same as taking the opposite order of the matrix multiplication. And not only that, if A and B commute, then I may as well treat A and B as just being regular numbers, and then we know that the exponential satisfies the fact that I can sum the objects in the exponent instead of multiplying the exponentials. Okay, so what does this mean? Well, I said every group element can be written in such a form, and this says that if I take the group multiplication of two elements, then the order does not matter. So this group is abelian. So this means that G is abelian. And what is more, the group multiplication in this Lie group G is now just the same as adding generators. So in the sense, we found a group isomorphism from the multiplications in G to the additions in this set of generators. So the group multiplication corresponds to addition in, okay, let's denote this tangent space by G with a small bar underneath. So in G. So what does this mean? So it means that as soon as your group is abelian and you know the generators, then you can really forget about the group and just look at the linear algebra of the generators. To get the multiplication of two elements, it is just fine to take your two vectors and add them up. Now, of course, this is not the general situation, otherwise Lie groups would be a bit too simple. In general, this identity does not hold. So in general, exponential of a times the exponential of b is not equal to the reverse exponential of b times the exponential of a, and it's also not equal to the addition of a and b. And in particular, this does not hold when the commutator of these matrices A and B does not vanish. Now, one should note that you often encounter these kinds of multiplication of exponentials when you do have matrices that commute, in particular if they're just linear multiples of each other. Although we do have the exponential, say, of linear multiples of a times the exponential of another linear multiple of a is going to be the sum of those linear multiples by the same reasoning as for the abelian group. And in particular, this means by setting, say, lambda equal to 1 and mu equal to -1, such that here the exponent vanishes, so I get the identity matrix, that I find that the inverse of e to the power a is e to the power minus a. So e to the power a inverse element is really e to the power minus a. But for general group elements, it's not clear what the outcome is going to be. So what does this mean? So I told you that the exponential map is useful to transfer things from the group to the tangent space and back again. So it would be nice to actually understand the group structure here just in terms of the generators. And clearly just adding generators is not going to do this trick. It's not going to contain all the information that is contained in the group structure, because this equality is not satisfied. So we need some additional piece of mathematical structure on the tangent space that is going to encode the group multiplication. And this is the structure of a Lie algebra. So let's give the definition. A Lie algebra let me write that a bit more clearly. A Lie algebra which I like to denote by G with a little bar underneath. So this is my handwritten version of Fraktur font that you usually use in print. It is a vector space together with a Lie bracket. So some kind of square bracket that satisfies a number of axioms, just like the group multiplication had to satisfy. So let me list them explicitly and then go through. So the first one is closure, which is saying that if I have two vectors in my vector space G, and I look at the bracket of these two, that they are also in this vector space. Linearity, which is saying that if I look at the bracket of some linear combination of vectors, say in one of its slots, with another vector z, then it's going to expand linearly in this. So this is going to be a of x with z plus b of y with z. Antisymmetry, which is just saying that if I look at the Lie bracket of x with y, it is minus the reverse order. And then finally, we require the Jacobi identity, which says something about the compatibility when I compose the Lie bracket twice. So I take three elements, x, y, and z. Then I look at the bracket of x with the bracket of y and z, and I add the cyclic permutations of x, y, and z. So y with the bracket of z and x plus z with the bracket of x and y has to vanish. So whenever I have a vector space, G together with such a bracket satisfying these properties, I call it the Lie algebra. And now the claim is that naturally, whenever I have a Lie group, then the tangent space at the identity has such a Lie bracket satisfying these properties. And actually, this is not too difficult to check. And the thing that makes this easy is that we're always working in a representation. So for us, the Lie algebra G, which is going to be this linear combinations of the generators, are always going to be square matrices. So if G consists of square matrices, then there is a natural way to define the Lie bracket via just a commutator of these matrices. Then I can take x of y Lie bracket just to be the commutator, so xy minus yx. And it's easy to check now that the properties 2, 3, and 4 are actually identically satisfied just by the definition of this bracket. So 2, 3, and 4 are then automatically satisfied. Just by the properties of matrix multiplication. And the fact that the Jacobi identity is satisfied for the commutator, it's something that you can just check by working out the brackets here, and this you will do in an exercise. Okay, so the only real non-trivial point that we have to show is that whenever you take the commutator of some generators of a Lie group, that it is again a generator. And this will really capture the non-trivial information about the group multiplication structure. Okay, so let's do this. Let me leave the picture. Right, so this closure property, it should really capture non-trivial group multiplications. So whenever the group is not abelian. I mean, note that if the Lie group is going to be abelian, meaning that the generators are going to commute with each other, well then the Lie bracket is always going to vanish. So trivially, the Lie bracket is then part of the Lie algebra. So this property is going to be non-trivial when my Lie group is non-abelian. So what does it mean for a Lie group to be non-abelian? So if G is non-abelian, well, it means that if I take my group elements, so say e to the a, e to the b, it depends on the order of the multiplication. So in particular, I know that if I, okay, so this means that we have this for general kind of generators a and b, but let's move these exponentials to the other side using the fact that the inverse of the exponential is just the exponential of minus. So then I get, by multiplying by the exponential of minus b, I get this, and then the exponential of minus a, I get that this is not the identity in the group. But we do expect that if a and b are generators that are not too large, that this failure of the commutation of the exponential of a and the exponential of b is going to be fairly close to the identity element. And whenever you're fairly close to the identity element, it has to be of the form of the identity plus, again, a commutator. So that's where this Lie bracket is going to appear. So to make this more precise, what we're going to do is we're going to take these a and b to be small. So instead of taking them to be fixed vectors, let's look at the combination minus epsilon a into minus epsilon b. So we just multiply a and b with some small real number epsilon. And let's just see what this group element is going to be. Because we know that these are exponentials of generators, so they're genuine group elements. And I'm taking the multiplication of group elements, so this has to be a group element. Right? So it is an element of the group. And the same is true if I multiply everything by epsilon. So let's see what group element this is by performing the expansion. So here we're going to expand these exponentials using the definition of the matrix exponential to second order in epsilon. So I get, for the first factor, I get this, and for the second factor I get minus epsilon b plus 1/2 epsilon squared b squared. Then I get 1 plus epsilon a plus 1/2 epsilon squared a squared, 1 plus epsilon b plus 1/2 epsilon squared b squared, and then some terms of third order in epsilon. And let's just work out the brackets. Order by order in epsilon. So at 0th order in epsilon, I just have the identity matrices. So I get the identity matrix. At first order in epsilon, I get here minus a, minus b, plus a, plus b. So that vanishes. So there is no first order term in epsilon. So the first non-trivial term that I get here is going to be something proportional to epsilon squared. So let's collect all these terms. So the epsilon squared terms, they can come from the epsilon squared terms in these parentheses, or the cross terms of the linear terms. So let's collect the quadratic pieces first. So I get a 1/2 a squared from this one, plus 1/2 b squared, plus 1/2 a squared, plus 1/2 b squared. Okay, and now I look at the cross terms. So I start here. I get minus a times minus b, so plus ab, minus a times plus a, so minus a squared, minus a plus b, so minus ab. Okay, of course I had to, okay. Then I take minus b times plus a, so minus b a, minus b plus b, so minus b squared. So let's see what is left here. So I get 1/2 plus 1/2 minus 1 of the a squared, so these terms cancel. Get 1/2 b squared plus 1/2 b squared minus b squared. Here I have ab minus ab. And there you go. I forgot the term, which is the last term, so the cross term of the last two factors. So I had the plus a plus b, so that is plus ab. Okay? Plus something of order epsilon to the third. So to summarize, I have the identity plus the first contribution is going to be the commutator of a and b at order epsilon squared. Okay? But really this is like the definition of the generators. I look at an element close to the identity element, and if I take epsilon to be close to infinitesimal such that I can neglect all higher order terms, then I get a tangent vector, which is just the commutator of a and b. So this implies that this has to be a generator, or a linear combination of generators. So this has to be in the Lie algebra G. Okay, so that shows the closure of the Lie algebra. So now we see that for any Lie group we get a Lie algebra. And it is actually not so hard to see that as soon as you have a Lie algebra, you can completely reconstruct your Lie group. And this uses the nice formula. So the Lie algebra structure completely encodes the Lie group structure via the Baker-Campbell-Hausdorff formula. Let me switch to a different pen before it becomes unreadable. Which expresses the matrix multiplication of the exponential of two matrices as the exponential of some matrix. So it's the exponential of a plus b, but we said that this could not be true in general, so there are corrections terms. but they're all expressed in terms of the commutator. The first correction term is a plus 1/2 commutator of A with B. And then there are higher order corrections, so you get a plus 1/12 A B, and then minus 1/12 B of A with B, plus even higher order commutator terms. So these are multi-commutators, if you like. So how does this encode the full Lie group structure? So we know the set of generators, so we know the linear space in which A and B live, and we know the Lie bracket of all such generators. So in particular, we also know the multi-commutators. Since every Lie group element can be written as the exponential of A, we can just work out from this formula what the group multiplication of two general elements is going to be. Although in practice, of course, writing down an infinite number of multi-commutator terms is a bit painful. Okay. Now the last thing I want to stress is, so it's the second point on the menu, is a convenient way to summarize this Lie algebra structure, and therefore also the Lie group structure via this formula. Okay, so the Lie algebra structure is conveniently summarized in the following. So let me give a definition. The structure constants which are in general complex numbers, or actually real numbers with 3 indices of a n-dimensional Lie group with generators xa, so meaning that A runs from 1 up to n. The structure constants are determined by the relation that if I take the commutator of generators xa and xb, so because we know that they form a Lie algebra, this has to be part of the Lie algebra again, so it has to be a linear combination of generators. And the structure constants are exactly the coefficients in this linear combination, where the sum over C is implied here. So let me just give you a couple of remarks about the structure constants. So the first thing is that the structure constants do not depend on the representation that you're working in. So why is that? Well, we have determined these kind of the Lie algebra structure by looking at the composition of general group elements. And the way in which group elements compose, that is really a property of the abstract group. So meaning that this compositional structure is invariant under going from one group to an isomorphic group. Okay, so they really capture the compositional structure of the group. Although you should note that these are not really universal numbers in the sense that they still depend on the basis that I've chosen for my tangent space. Although they do depend on the basis of generators. But this choice of basis of generators is really something that is detached from your choice of representation. And note that if you would choose a different basis of generators, then these numbers f, a, b, c, they really transform in the way that you would expect from a tensor with 3 of these indices. Meaning that the similarity transform, it will be a matrix that has 2 indices. So the transformed structure constants will then correspond to contracting each of these 3 indices with my similarity matrix. So there are 2 properties of the structure constants that one can read off directly from the definition of the Lie algebra. The first one is that these things are antisymmetric in the first 2 indices, which is just saying that the Lie bracket is antisymmetric. And also the Jacobi identity says something non-trivial about the structure constants. I'm not sure I want to write this down explicitly. I think you're going to do this in the exercises too. So the Jacobi identity implies that if I do this particular contraction of the structure constants A, B, D, C, D, E, that it's 0. So these structure constants, they are primarily used in the physics literature if you want to just specify a group and work with the linear algebra of the generators. Then it's just useful to explicitly know what these numbers are. So for instance, they appear when you're looking at scattering amplitudes of particles in the standard model, where the structure constants are then the structure constants of the gauge groups of the standard model. So SU3 and SU2. So they appear all over the place in these amplitudes. Okay,